is buoyed up by a force equal to the weight of the fluid it displaces. Oh, thank you. That's why this life vest keeps me afloat, and that's why that there kayak floats. In fact, that's why anything that floats, floats. This guy paddling in, back behind me here, is Adam Boyd. Now, Adam is 18, and he finished in the top 10 of the men's U.S. Olympic trials, finished second overall in the C1 competition at the Potomac Whitewater Festival. And recently, Adam was down in Agua Azul, Mexico, where he came across Postcard Falls, a 55-foot waterfall.
Howdy.
How's it going?
Pretty good.
So did you suffer any bodily damage going over that waterfall?
Nope, I was all right.
No broken bones or collapsed lungs?
No problem.
Well, that's good. That's good to hear. So tell us a little bit about this here kayak.
Well, this is a dagger kayak. It's made out of plastic. It's hollow throughout, filled with air. And this here we have what we call a spray skirt. Keeps the air in and the water out.
So you do go underwater sometimes, though, like say you go over falls or you're into rapids.
It'll go under, yeah. The water will push you under, but they're designed to bring you right back up to the surface.
So this baby here, this baby right here, this floats pretty good, right?
It floats really good.
This floats really good. Just that tiny little kayak supports itself and Adam. Why? Why does this pie plate float? And this one? Sink. The answer is specific gravity. Specific gravity is how we figure out whether something is going to float or not, and how much weight we can put on it before it sinks. Let's start with displacement. So if we dig a hole in the ground, what have we done?
Well, we've displaced the dirt. There used to be dirt here, and now there's not. Now
there's a hole. That's displacement. So let's see if we can try to dig a hole in the water. You can't do it, right?
The water keeps rushing back in.
Right, because of the fluid nature of liquid, when you displace it, the liquid wants to push back into that area. It's okay, though. The water pushing back in has a force. We call it the buoyant force. Now, the buoyant force is what makes something float. But there actually is a way to dig a hole in water. Did you ever notice what happens to a bathtub when you fill it all the way to the top and get in? This is because the space my body is taking up used to be filled with water. By getting in, I've displaced an amount of water equal to the volume of space my body is taking up. I've created a hole in the water. Now, the more space we take up in the water, come on, everybody. The more water we displace. I just want to say I feel so much love in this pool right now. Okay, everybody out. Now check it out. When I got in, this pool was full. Look how much water we've displaced just by the volume of all of our bodies. When you go into a river, you're displacing an amount of water equal to the weight of your body. So the river level rises by that much. Because my body and this life vest made a hole in the water, and because the water wants to push back into that hole, the buoyant force is equal to the weight of the water I'm displacing. If we collected the water I displaced when I got into the pool and weighed it, we would have a figure for the buoyant force the water was exerting on me. So, how much does water weigh? Well, let's find out. We could use...
Well, a cubic foot of water weighs about 62 pounds.
Oh, wait a second, excuse me. About? What's this about stuff? We need to be exact here. Exact!
Well, the water's density depends on a lot of stuff. Like if it's salt water or fresh water, even the temperature. But a good average to use is 62 pounds per cubic foot.
Okay, wow. Well, then that means this river must weigh...
A lot.
Oh! Just kidding. I'm fine. I'm fine, really.
All right, that's good.
So you see, whether something floats or not doesn't have anything to do with how much it weighs, but everything to do with how much the fluid it displaces weighs. You see, this coconut here weighs more than this rock, but the coconut will float, even though it weighs more. Okay, here's how it works. All right, are you ready? Ready back there? All right. These two pie plates are exactly the same. The only difference is this. When I place this in the water, it displaces some of the water. Gravity is pulling the pie plate down, but the water is pushing back with a buoyant force equal to the weight of the water displaced. If the weight of the water displaced isn't greater than the weight of the object, it sinks. But. If we increase the amount of water displaced, the force pushing back against the object is increased, and it floats even though it weighs the same and is made of the same material as the pie plate that sunk. That's Archimedes' principle. So we end up with a ratio between the weight of an object and the weight of the fluid it displaces, and this ratio is called specific gravity. Now, if an object has a specific gravity of less than 1, it'll float. If it's greater than 1, it sinks. Okay, so let's figure out why this puppy floats.
Oh, all right.
Okay, good. So, first thing we gotta do is figure out how much water this kayak is gonna displace. So, let's start by figuring out the dimensions of the part of the kayak that's in the water, okay?
All right.
All right, good. Measurement here. So, do you want a tapered cut with this baby? Does that sound all right?
Sounds great.
Yeah, we can put some wings on it for you if you want. Okay. Could you hold this right? I'll be back in just a second. Yeah. All right, 42, perfect. All right, that looks good. You okay?
Good.
Okay, cool. The part of the kayak that's underwater is 5 feet long by 2 feet wide by 6 inches deep. To find the volume, we just multiply. That gives us 5 cubic feet. So, how much does this kayak weigh?
About 40 pounds.
All right, and how much do you weigh?
150.
All right, okay, so that means the kayak has to displace at least 190 pounds to float. Okay, so if we have 5 cubic feet at 62 pounds per cubic foot, that's 310 pounds of buoyant force, which is a ratio of 0.61, which is less than 1. So this kayak will float with you in it.
Well, I already knew that.
But you didn't know why. A kayak is basically a sealed container. As long as it maintains its volume of air inside the hull, it's going to have a specific gravity that will keep it coming back up to the surface.
Hey Greg, how come fish don't float or sink?
Well, I'm glad you asked, Courtney. You see, fish have something we call neutral buoyancy.
Because the weight of the water they displace is roughly equal to their own weight, they don't sink or float. That's why scuba divers wear weight belts. To cancel out their natural buoyancy, they add weight until they're neutral.
Here, Greg, can you hold this for a sec?
Yeah, sure.
I had a goldfish that floated once. He was dead.
Oh, okay. Well, we're not actually talking about dead goldfish today, but thanks. Thanks for sharing.
Ships are made of pretty heavy materials, steel, well, even concrete. The reason they float is the airspace inside the hull takes up volume, and that makes sure the specific gravity is less than 1. If the hull springs a leak, the air is replaced by water, which is heavy, and it fills until the specific gravity is greater than 1, and it sinks.
Are we rolling?
Mm-hmm.
Okay.
Hi, I'm John Kazimirchik, owner of Millbrook Boats. I design and build whitewater canoes and kayaks.
How much someone weighs, how does that affect the construction of the boat?
The fastest boats are the narrowest boats. Unfortunately, for a heavier person, that might not be true, so a heavier person has to get his buoyancy from somewhere else. The kayak might be made deeper. The depth of the boat would make up the buoyancy in the vertical plane rather than the width of the horizontal plane.
So, John, the old Archimedes principle must be pretty important to you.
It's certainly the focal point of a boat builder, yeah. Without it, you'd be sunk.
Who said that?
So that's it. I'd like to thank Adam Boyd and the rest of the kayakers who helped us today. Courtney, Brendan,
All right, that's good.
Silas, and Kyle.
Well,
I'd also like to thank Peter Kennedy and Bill Farley from Adventure Quest. Now, I don't know, I'm gonna go out on a limb here, but I'd venture to say that our specific gravity, I think it's more than 1. What do you guys think?
yeah.
Yeah?
Definitely.
I think it's more than 1. We're not going anywhere.